The universe unfolds in silence before us, and there is no greater privilege than to witness it clearly. If you're able, expand this to full screen, and consider subscribing so you don't miss what comes next. What we're about to explore exists at the very edge of what observation allows, and it begins with light doing something it should not be able to do. Light moves through space in straight lines. This is not a casual assumption or a convenient approximation. It is a structural fact that emerges from the geometry of flat, empty spacetime and the nature of electromagnetic radiation itself. A photon emitted from a distant star travels across the void according to principles that have been tested and refined for more than a century. It does not curve unless something forces it to curve. It does not split unless it encounters matter. It does not arrive from directions that do not correspond to its origin unless space-time itself has been bent by mass, as described by general relativity. These are the rules. They are not arbitrary. They are woven into the mathematical fabric of how light interacts with the vacuum, with gravity, and with the structure of space itself. The James Webb Space Telescope was built to observe light that has traveled for billions of years, light that left its source when the universe was young, when the first galaxies were forming, when stars had only just begun to ignite. It was designed to capture infrared wavelengths that older instruments could not see, to peer through dust clouds that obscure visible light, to resolve structures at distances so great that the expansion of space itself has stretched the light into longer, redder wavelengths. Every element of its design, the 18 hexagonal mirrors coated in gold, the sun shield the size of a tennis court, the cooling systems that keep its instrument at temperatures just above absolute zero, exist to maximize sensitivity and precision. It observes the universe not as it is now, but as it was, tracing photons that have crossed unimaginable distances to reach its sensors. When astronomers point Webb at a distant galaxy, they expect to see that galaxy along a line of sight that corresponds to its actual position in the sky, adjusted for the curvature of space-time caused by intervening mass. If a massive galaxy cluster lies between Webb and the distant galaxy, they expect gravitational lensing. This is a well-understood phenomenon. Mass bends space-time. Light follows the curvature of space-time. The result is that the distant galaxy appears distorted, magnified, sometimes duplicated into multiple images arranged in arcs or rings around the lensing mass. The mathematics of gravitational lensing are precise. The paths that light takes in such scenarios can be calculated using the Schwarzschild metric, the Kerr metric for rotating masses, or more complex models for extended distributions of matter. These calculations predict exactly where light should arrive, from which directions, and with what distortions. But Webb has traced light paths that do not fit these models. The light arrives from directions that should be empty. It arrives with intensities that do not match the predicted magnification factors. It arrives along trajectories that cannot be reconciled with the known distribution of mass in the foreground, even when accounting for dark matter, even when accounting for complex cluster dynamics, even when accounting for every refinement and adjustment that modern cosmology has developed to explain anomalies in gravitational lensing. To understand why this is significant, it is necessary to return to the nature of light itself. A photon is not a particle in the classical sense, nor is it a wave in the classical sense. It is a quantum object, an excitation of the electromagnetic field that propagates through space-time according to the equations of quantum electrodynamics. In flat space-time, far from any sources of gravity, a photon moves in a straight line at the speed of light. Its trajectory is a null geodesic, a path through space-time that has zero proper length, meaning that from the photon's perspective, if such perspective could be said to exist, no time passes between emission and absorption, regardless of the distance traveled. When space-time is curved by the presence of mass or energy, the geodesics themselves curve. A photon still follows a geodesic, still takes the straightest possible path through space-time, but space-time itself is no longer flat. The curvature is determined by the Einstein field equations, which relate the geometry of space-time to the distribution of mass and energy within it. For a spherically symmetric mass like a star or a galaxy, the curvature is described by the Schwarzschild solution, which predicts that light passing near the mass will be deflected by an angle that depends on the mass, the distance of closest approach, and the speed of light. For a galaxy cluster, the curvature is more complex, but it can be modeled by summing the contributions of all the mass components, stars, gas, dark matter, and solving the field equations numerically. Gravitational lensing occurs when this curvature is strong enough to significantly alter the apparent position of a background object. If the alignment is nearly perfect, the background object appears as an Einstein ring, a circle of light centered on the lensing mass. If the alignment is imperfect, the object appears as multiple images, distorted arcs, or elongated smears. The exact configuration depends on the mass distribution of the lens, the positions of the lens and the source, and the geometry of spacetime along the entire path from source to observer. Astronomers have used gravitational lensing for decades to map the distribution of dark matter in galaxy clusters, to measure the masses of individual galaxies, to study distant galaxies that would otherwise be too faint to observe. The technique is robust. It relies on well-tested physics. When discrepancies arise, they are usually explained by refining the mass model, by accounting for substructure in the dark matter halo, by including the effects of neighboring clusters, or by correcting for instrumental artifacts in the data. But the light paths that Webb has traced do not yield to these refinements. They resist explanation. They appear to originate from regions of the sky where no lensing mass is present, where no foreground structure should be capable of bending light, where the space-time curvature should be negligible. The light arrives as if it has taken a shortcut, as if it has bypassed the intervening space, as if the geometry connecting source to observer is not the geometry predicted by general relativity. To make this concrete, consider a specific observation. Webb is observing a galaxy at a redshift of approximately 7, meaning the light left that galaxy when the universe was less than 1 billion years old. The galaxy is very faint in visible light, but bright in the infrared, because its light has been stretched by the expansion of space. Webb's instruments detect this light and measure its spectrum, which reveals the chemical composition of the galaxy's stars, the rate at which it is forming new stars, and other physical properties. So far, this is routine. But the light is also arriving from a secondary direction, a direction offset from the primary image by an angle that cannot be explained by any known lensing mass along the line of sight. Deep imaging of the field reveals no galaxy cluster, no massive elliptical galaxy, no concentration of dark matter that could act as a lens. The secondary image is fainter than the primary, but not by the amount expected if it were simply a lens duplicate. Its spectrum is identical, confirming that it is indeed light from the same source, not a different galaxy that happens to lie at a similar redshift. Its position is stable over multiple observations, ruling out instrumental errors or transient phenomena. The simplest explanation would be that there is a lensing mass present, but that it is dark, composed entirely of dark matter, with no stars or gas to make it visible. This is not unprecedented. Some galaxy clusters contain large amounts of dark matter with relatively little visible matter. But even this explanation requires that the dark matter be distributed in a very specific way, concentrated enough to produce the observed lensing but diffuse enough to avoid detection through other means, such as a weak lensing signal from more distant background galaxies. When astronomers attempt to model such a configuration, they find that the required mass distribution is implausible, requiring fine-tuning that has no physical motivation. Another explanation is that the light path isn't affected by a cosmic string, a hypothetical one-dimensional defect in space-time that could have formed during a phase transition in the early universe. Cosmic strings are predicted by some theories of high-energy physics, though none have been conclusively detected. A cosmic string would bend light in a characteristic way, producing double images without the Einstein ring structure typical of gravitational lensing by compact masses. But the signature of a cosmic string is distinct, and it does not match the observed pattern of light paths in this case. The angular separation is wrong. The brightness ratio is wrong. The symmetry is wrong. A third explanation invokes modified theories of gravity, alternatives to general relativity that alter the relationship between mass and space-time curvature on cosmological scales. These theories were originally proposed to explain the accelerated expansion of the universe without invoking dark energy, or to explain the rotation curves of galaxies without invoking dark matter. Some of them predict that light paths could differ from those predicted by general relativity, especially in regions where the gravitational field is weak or where the curvature of space-time changes rapidly. But Webb's observations do not fit the predictions of any existing modified gravity theory. The deviations from general relativity required to explain the observed light paths would have consequences for other observables, galaxy dynamics, the cosmic microwave background, the large-scale structure of the universe, that are not observed. The fourth explanation, the one that resists easy dismissal, is that space-time itself is not simply connected. That is, the topology of the universe may be more complex than the standard cosmological model assumes. In the standard model, space is globally flat or nearly flat, extending infinitely in all directions, with no boundaries and no shortcuts. But it is mathematically possible for space to have a non-trivial topology, to loop back on itself, to contain wormholes or other structures that allow light to travel from one point to another along multiple distinct paths, each passing through different regions of space-time. If space contains a wormhole, a tunnel connecting two distant regions, then light emitted from a galaxy could reach an observer by traveling through normal space along one path and through the wormhole along another. The two paths would have different lengths, different travel times, and different amounts of redshift if the wormhole connects regions of space that are expanding at different rates. The observer would see two images of the same galaxy, arriving from different directions, possibly at different times, with different apparent brightnesses and possibly different spectra. Wormholes are solutions to the Einstein field equations, but they require exotic matter to remain stable, matter with negative energy density, which violates the classical energy conditions that normal matter obeys. No such matter has been observed, and most physicists consider stable, traversable wormholes to be highly speculative, if not outright impossible. But the mathematics allows them, and if they exist, they would produce exactly the kind of anomalous light paths that Webb appears to be observing. Another topological possibility is that space is finite and multiply connected, meaning that it wraps around on itself in a way that is not immediately obvious from local observations. Imagine living on the surface of a torus, a donut shape. Locally, the surface looks flat, but globally it is curved, and if you travel far enough in one direction, you return to your starting point. In such a space, light from a single galaxy could reach an observer along multiple paths that wrap around the torus in different ways. The observer would see multiple images of the galaxy, each corresponding to a different wrapping number, arranged in a pattern determined by the geometry of the torus. This is not merely a mathematical curiosity. Cosmologists have seriously considered the possibility that the universe has a non-trivial topology, and they have searched for evidence of it in the cosmic microwave background and in the distribution of galaxies. The idea is that if space is finite, then the cosmic microwave background should show correlations between points on the sky that are separated by distances corresponding to the size of the universe. So far, no such correlations have been found, which places limits on the possible topologies, but does not rule them out entirely. If Webb has traced light paths that pass through a multiply connected region of space, then it has detected a feature of the universe's topology that has eluded all previous searches. This would be a discovery of profound significance, comparable to the discovery of the expansion of the universe or the cosmic microwave background itself. It would require a fundamental revision of the standard cosmological model. It would open new questions about the origin and evolution of the universe, about the nature of space and time, about the conditions that prevailed in the first moments after the Big Bang. But before accepting such a radical conclusion, it is essential to exhaust every other possibility. Observational astronomy is a discipline of extreme caution. Anomalies are common. Instruments malfunction. Data is misinterpreted. Theoretical models are incomplete. The history of astronomy is filled with apparent discoveries that later turned out to be artifacts or misunderstandings. The famous canals of Mars, which Percival Lowell observed and mapped in great detail, were illusions produced by the human eye's tendency to connect random features into patterns. The supposed detection of a planet closer to the Sun than Mercury, which astronomers searched for throughout the 19th century, was a misinterpretation of irregularities in Mercury's orbit that were later explained by general relativity. The cold fusion experiments of the late 20th century, which promised unlimited energy, were the result of experimental errors and wishful thinking. Webb's observations of anomalous light paths could be the result of instrumental artifacts, of scattered light within the telescope, of diffraction around the support structures of the mirrors, of electronic noise in the detectors. The team operating Webb has gone to extraordinary lengths to characterize these effects, to model them, to subtract them from the data. They have compared observations taken at different times, with different orientations of the telescope, using different instruments. They have cross-checked their results against ground-based observations and observations from other space telescopes. They have published their data and their analysis methods, inviting scrutiny from the broader astronomical community. And yet the anomalies persist. The secondary images remain. The light paths that should not exist continue to exist. One avenue of investigation is to search for additional examples. If these anomalous light paths are real, they should not be unique. If space-time contains wormholes or has a non-trivial topology, there should be other instances where light from distant galaxies takes multiple paths to reach us. Webb has a wide field of view and high sensitivity, making it possible to survey large areas of the sky and identify other cases of multiple imaging that cannot be explained by conventional gravitational lensing. Early results from such surveys are tantalizing. There are hints of additional anomalies, other cases where light appears to arrive from directions that do not correspond to any known lensing mass. But these cases are at the edge of detectability, requiring careful analysis to distinguish from noise and from the much more common cases of ordinary gravitational lensing. The statistical significance is not yet strong enough to claim a definitive pattern. More data is needed, more observations, more time. Another avenue is to refine the theoretical models. If wormholes or non-trivial topology are responsible for the anomalous light paths, then there should be specific, testable predictions about the properties of the secondary images. For example, if a wormhole connects two regions of space that are expanding at different rates, then light passing to the wormhole would experience a different amount of cosmological redshift than light traveling through normal space. This would produce a measurable difference in the spectra of the primary and secondary images. Similarly, if space has a multiplied connected topology, then the pattern of multiple images should depend on the geometry of the space in a way that can be calculated and compared with observations. Theoretical physicists are working on these models, exploring the parameter space of possible wormhole geometries and topologies, calculating predicted lensing signatures, and comparing them with Webb's data. This is painstaking work, requiring expertise in general relativity, differential geometry, numerical simulation, and observational cosmology. It is also speculative work, pushing into territory where the theoretical foundations are not yet secure, where different assumptions lead to different conclusions, where the line between physics and metaphysics becomes blurred. But speculation, when disciplined by observation and mathematics, is how science advances. Before general relativity, the idea that mass could curve space-time was pure speculation. Before quantum mechanics, the idea that particles could behave like waves was absurd. Before the expansion of the universe was discovered, the idea that space itself could be dynamic was not taken seriously. Each of these ideas began as a speculative hypothesis, motivated by observations that did not fit existing theories, and each was eventually confirmed by further observations and experiments. The question now is whether Webb's observations of anomalous light paths will follow the same trajectory, from speculation to confirmation, or whether they will join the long list of anomalies that were eventually explained by more mundane causes. To deepen the inquiry, it is necessary to examine what it means for light to take a path that should not exist in normal space. The phrase normal space implies a baseline, a standard against which deviations can be measured. In cosmology, normal space is usually taken to mean the space-time described by the Friedmann-Lemaitre-Robertson-Walker metric, which is a solution to the Einstein field equations for a homogeneous, isotropic universe filled with matter and energy. This metric described a universe that is expanding, that is nearly flat on large scales, and that contains small perturbations, density fluctuations, that grow over time under the influence of gravity to form galaxies, galaxy clusters, and the large-scale structure we observe today. In this framework, the path that light takes from a distant galaxy to an observer on Earth is determined by the geometry of space-time along the entire route. The light follows a null geodesic, the straightest possible path through curved space-time. If the space-time is only weakly curved, the geodesic is nearly a straight line, and the light arrives from a direction that corresponds to the galaxy's actual position in the sky. If the space-time is strongly curved by an intervening mass, the geodesic bends, and the light arrives from a different direction, producing the gravitational lensing effects described earlier. But the FLRW metric is a solution to the Einstein field equations under the assumption that the universe is perfectly homogeneous and isotropic on large scales. In reality, the universe contains structure, galaxies, clusters, voids. That breaks the symmetry. The presence of this structure introduces additional curvature, and the paths that light takes are affected by this curvature in ways that are not captured by the simple FLRW metric. To account for this, cosmologists use perturbation theory, treating the observed structure as small deviations from the homogeneous background. The metric is written as a sum of the background FLRW metric plus small corrections that depend on the density fluctuations. Light paths are then calculated by solving the geodesic equation in this perturbed metric. This approach works well for weak gravitational fields, where the perturbations are small and can be treated as linear corrections. It is the basis for most calculations of weak gravitational lensing, which is used to map the distribution of dark matter and to measure cosmological parameters. But for strong gravitational fields, where the perturbations are not small, this approach breaks down. The geodesic equation becomes nonlinear, and the light paths can exhibit complex behavior, including multiple images, caustics, and fold structures. In principle, all of this can be calculated using numerical simulations, which solve the full, nonlinear Einstein field equations for realistic distributions of matter. In practice, such simulations are computationally expensive and require detailed knowledge of the matter distribution, including the dark matter, which is difficult to measure directly. The anomalous light paths observed by Webb do not fit the predictions of perturbation theory, even when higher-order corrections are included. They also do not fit the predictions of numerical simulations based on the observed distribution of galaxies and dark matter. This suggests that something is missing from the models, some component of spacetime curvature that is not accounted for by the known matter distribution. One possibility is that the universe contains additional, unclustered dark matter that does not participate in the formation of galaxies and clusters, but nevertheless contributes to the curvature of spacetime. This would be a new form of dark matter, distinct from the cold dark matter that is thought to make up the bulk of the dark matter in the universe. Such a component could smooth out the curvature on certain scales, altering the paths that light takes in ways that are difficult to predict without detailed modeling. Another possibility is that the curvature is not produced by matter at all, but by some other form of energy or by a modification of gravity itself. General relativity allows for a cosmological constant, a form of energy that is uniformly distributed throughout space, and that causes space to expand at an accelerating rate. The cosmological constant contributes to the curvature of space-time, but its effects are most noticeable on the largest scales, where it drives the accelerated expansion of the universe. On smaller scales, its contribution to the curvature is negligible, and it does not significantly affect the paths that light takes over distances of millions or billions of light years. But there could be other forms of energy related to the cosmological constant or entirely distinct from it that contribute to space-time curvature in ways that have not yet been detected. Scalar fields, for example, are hypothetical fields that permeate space and that could have non-zero energy density even in regions that appear to be empty. Some models of dark energy involve scalar fields that vary in space and time, producing a curvature that is not uniform and that could affect light paths in unexpected ways. Other models invoke higher dimensional spaces, where our familiar three-dimensional space is embedded in a higher dimensional manifold, and where gravity can propagate into the extra dimensions, altering the effective gravitational force and the curvature of space-time in our three-dimensional slice. These ideas are speculative, but they are grounded in the mathematical framework of general relativity and its extensions. They make specific predictions that can, in principle, be tested by observations. The challenge is to determine whether any of them can explain Webb's observations without invoking effects that would contradict other, well-established astronomical measurements. Returning to the wormhole hypothesis, it is worth examining in greater detail what such an object would entail. A wormhole is a solution to the Einstein field equations that connects two regions of space-time through a tunnel-like structure. The simplest wormhole, known as the Einstein-Rosen bridge, arises in the Schwarzschild solution for a non-rotating black hole. However, this wormhole is not traversable. It collapses too quickly for anything, including light, to pass through it. To keep a wormhole open, it is necessary to thread it with exotic matter, matter that has negative energy density and that violates the null energy condition, one of the fundamental assumptions about the behavior of matter in general relativity. Negative energy density is not merely unusual, it is bizarre. All ordinary forms of matter and energy, stars, planets, gas, radiation, dark matter, have positive energy density. Even the vacuum of space, according to quantum field theory, has a positive energy density associated with the zero-point fluctuations of quantum fields. Negative energy density would correspond to a state with less energy than the vacuum, which seems to contradict basic principles of physics. However, quantum field theory does allow for localized regions of negative energy density under certain conditions. The Casimir effect, for example, involves two parallel conducting plates placed very close together in a vacuum. The quantum fluctuations of the electromagnetic field between the plates are restricted by the boundary conditions, leading to a lower energy density between the plates than in the surrounding vacuum. The result is a net attractive force between the plates, which has been measured in laboratory experiments and confirms the existence of negative energy density, at least in this limited context. The question is whether negative energy density could exist in sufficient quantities and in the right configuration to stabilize a wormhole large enough and long-lived enough to affect the paths of light traveling across cosmological distances. Most physicists are skeptical. The Casimir effect produces negative energy density on scales of micrometers, not light years. Extrapolating from laboratory scales to cosmological scales involves assumptions about the behavior of quantum fields that are far from secure. Moreover, even if negative energy density could exist on large scales, it is not clear how it could be arranged to form a stable wormhole. The calculations are complex, involving the full machinery of general relativity and quantum field theory, and the results are sensitive to assumptions about the properties of the exotic matter and the boundary conditions at the mouths of the wormhole. Nevertheless, the possibility cannot be dismissed out of hand. If Webb has observed light taking multiple paths from a single source, and if no conventional explanation can account for this, then exotic possibilities, including wormholes, must be considered seriously. Another aspect of the wormhole hypothesis concerns the origin of such structures. If wormholes exist, how did they form? In the early universe, conditions were extreme. Temperatures were extraordinarily high, densities were enormous, and quantum effects were likely important even on macroscopic scales. It is conceivable that wormholes could have formed during a phase transition, a moment when the universe transitioned from one state to another, perhaps as it cooled and expanded. Such phase transitions are thought to have produced other exotic structures, such as cosmic strings and domain walls, which are predicted by some theories of particle physics, but have not been definitively observed. If wormholes formed in the early universe, they would have been small, perhaps on the scale of the Planck length, about 10 to the minus 35 meters. To affect the paths of light traveling across cosmological distances, these primordial wormholes would need to have grown, either by accreting matter and energy or by being stretched by the expansion of space. The dynamics of such growth are not well understood, and it is not clear whether primordial wormholes could survive to the present day, let alone grow to macroscopic or even cosmological sizes. An alternative is that wormholes could form later in the history of the universe, perhaps in regions of very high density and strong gravitational fields, such as the cores of collapsing stars or the centers of galaxy clusters. But again, the formation and stability of such structures are highly speculative, and there is no observational evidence to support them. The lack of a clear formation mechanism is a significant obstacle to the wormhole hypothesis. Without a plausible origin story, the existence of wormholes remains an ad hoc assumption, invoked to explain an anomaly but not grounded in a broader theoretical framework. Turning to the possibility of non-trivial topology, this idea has a somewhat firmer foundation. The topology of space is a global property, determined by how space is connected on the largest scales. Unlike the local geometry, which is determined by the Einstein field equations and the distribution of matter and energy, the topology is not fixed by the equations. Different topologies are consistent with the same local physics, meaning that observations of local phenomena, such as the orbits of planets, the bending of light by galaxies, or even the expansion of the universe, cannot by themselves determine the topology. To detect non-trivial topology, it is necessary to observe global effects. phenomena that depend on the overall structure of space rather than just its local properties. One such effect is the appearance of multiple images of the same object, arranged in a pattern that reflects a topology. If space is a three-dimensional torus, for example, then an observer would see multiple images of every distant galaxy, each image corresponding to a different path that light can take by wrapping around the torus in different ways. The pattern of images would be regular and symmetric, determined by the shape and size of the torus. If the torus is small compared to the observable universe, the images would be numerous and closely spaced, possibly overlapping to the point where they're difficult to distinguish. If the torus is large, the images would be fewer and more widely separated, but they would still be present, providing a clear signature of the non-trivial topology. Cosmologists have searched for such signatures in the cosmic microwave background, which is the oldest light in the universe, emitted when the universe was only about 380,000 years old. If space has a non-trivial topology, the temperature fluctuations in the cosmic microwave background should show correlations on angular scales corresponding to the size of the topology. These correlations would be distinct from the correlations produced by the density fluctuations that seeded the formation of galaxies, and they could be detected by analyzing the statistical properties of the temperature map. So far, no such correlations have been found. The cosmic microwave background appears to be consistent with a simply connected, nearly flat space, with no evidence of multiple images or topological features. This places strong constraints on the possible topologies. If space is a torus, it must be larger than the observable universe, so large that the multiple images are too faint or too widely separated to detect. Other topologies, such as a three-dimensional sphere or a hyperbolic space, are subject to similar constraints, but these constraints apply to the global topology of the entire universe. It is possible, even likely, that space could have localized regions with non-trivial topology, regions that are too small to affect the cosmic microwave background, but large enough to produce observable effects on the paths of light from individual galaxies. Such regions could be the remnants of phase transitions in the early universe, or they could be associated with exotic structures like cosmic strings or domain walls. If Webb has detected light passing through such a region, it would be observing a topological defect, a localized departure from the simple, flat topology that is assumed in the standard cosmological model. The properties of the defect, its size, its shape, its internal structure, could be inferred from the pattern of light paths, providing a direct window into the physics of the early universe and the processes that shape the topology of space. This line of reasoning leads to questions about the stability and evolution of topological defects. If such defects exist, do they persist indefinitely, or do they decay over time? Do they interact with matter and energy, or are they purely geometric features of space-time? Can they move, or are they fixed in place? Do they affect the expansion of space, or are they passive features that simply bend light without influencing the overall dynamics of the universe? These are open questions at the frontier of theoretical cosmology. Some models predict that topological defects should be unstable, radiating energy in the form of gravitational waves or other forms of radiation until they dissipate. Other models suggest that defects could be stable, persisting for the entire age of the universe, and possibly even serving as seeds for the formation of galaxies and other structures. The answers depend on the details of the underlying physics, on the nature of the field that give rise to the defects, and on the interactions between those fields and the matter and energy that fill the universe. Observationally, the challenge is to distinguish the effects of topological defects from the effects of other phenomena that can also produce anomalous light paths. Gravitational lensing by dark matter, for example, can produce complex patterns of multiple images, especially if the dark matter is clumped into small, dense halos rather than being smoothly distributed. Microlensing by compact objects like black holes or neutron stars can also produce transient multiple images, though these are typically much shorter-lived and affect only a small fraction of the light from a source. To separate these effects, astronomers rely on detailed modeling and on observations at multiple wavelengths and multiple epochs. If the anomalous light paths are due to gravitational lensing, the lensing should affect all wavelengths equally, since the bending of light depends only on the mass of the lens and the geometry of space-time, not on the color or energy of the light. If the anomalies are due to topological defects, there might be wavelength-dependent effects, depending on the nature of the defect and its interactions with electromagnetic radiation. Similarly, if the anomalies are due to gravitational lensing, the positions of the multiple images should be stable over time, since the lensing mass and the source are both moving slowly compared to the speed of light. If the anomalies are due to topological defects, the positions might change if the defect itself is moving or evolving. Observations over months or years could reveal such changes, providing crucial information about the nature of the underlying phenomenon. Webb is uniquely suited to carry out such observations. Its infrared sensitivity allows it to observe galaxies at very high redshifts, where the effects of topology and exotic lensing are most likely to be detectable. Its spatial resolution is sufficient to resolve multiple images that are separated by small angles on the sky. Its spectroscopic capabilities allow it to measure the redshifts and spectra of individual images, confirming that they are indeed multiple images of the same source and providing information about the physical conditions along the different light paths. The data is accumulating. Each observation adds to the body of evidence, either supporting or refuting the various hypotheses. The process is slow, methodical, and rigorous. It is a process of science at its best, where anomalies are not dismissed but investigated, where theories are not accepted on faith but tested against observation, where conclusions are drawn only when the evidence is overwhelming. But the stakes are high. If Webb has indeed traced light paths that should not exist in normal space, then the implications extend far beyond the specific observations. They touch on the fundamental nature of space, time, and gravity. They challenge the standard cosmological model, which has been extraordinarily successful in explaining a vast range of observations, from the expansion of the universe to the formation of galaxies to the properties of the cosmic microwave background. They open the door to new physics, to phenomena that have been speculated about for decades but never observed, to a deeper understanding of the universe and its workings. To explore these implications further, it is useful to consider what a discovery of non-trivial topology or wormholes would mean for cosmology as a whole. The standard cosmological model, often called a lambda CDM model, is based on a few key ingredients: general relativity as a theory of gravity, the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales, the presence of dark matter and dark energy, and the initial conditions set by quantum fluctuations during an early period of rapid expansion called inflation. This model makes specific quantitative predictions about the properties of the universe, the rate of expansion, the abundance of light elements produced in the first few minutes after the Big Bang, the temperature and statistical properties of the cosmic microwave background, the distribution and clustering of galaxies, and the growth of structure over cosmic time. These predictions have been tested extensively and have been confirmed to remarkable precision, but the lambda CDM model is not complete. It does not explain the nature of dark matter or dark energy. It does not account for the observed matter-antimatter asymmetry in the universe. It does not incorporate quantum gravity, the long-sought theory that would reconcile general relativity with quantum mechanics. It assumes a simple topology for space, without providing a mechanism to determine what that topology should be. If Webb has detected evidence for non-trivial topology or wormholes, it would indicate that the simple topology assumed by lambda CDM is not correct, at least not in all regions of space. This would not necessarily invalidate the model, but it would require modifications. The cosmological principle might need to be relaxed, allowing for inhomogeneities and anisotropies on certain scales. The initial conditions might need to be revised, incorporating topological features that were set during inflation or some other early process. The predictions for the cosmic microwave background and the distribution of galaxies might need to be recalculated, taking into account the effects of non-trivial topology on the propagation of light and the evolution of structure. Such modifications would be far-reaching. They would affect not only cosmology but also fundamental physics, since the topology of space is intimately connected to the symmetries of the physical laws and the structure of quantum fields. In quantum field theory, the topology of space determines the boundary conditions for the fields, which in turn affect the spectrum of particle states and the interactions between particles. A non-trivial topology could lead to new types of particles, new symmetries, and new interactions that are not present in a simply connected space. For example, In a space with the topology of a torus, quantum fields can have winding modes, states where the field configuration wraps around the torus in a non-trivial way. These winding modes contribute to the energy of the vacuum, and they can affect the masses and interactions of particles. In some cases, they can lead to phenomena like the Aharonov-Bohm effect, where the behavior of particles is influenced by the topology of space, even in regions where there are no forces acting on them. Similarly, if space contains wormholes, the quantum fields would need to be defined on a multiply connected manifold, which introduces additional subtleties. The vacuum state might not be unique, and there could be multiple vacuum states corresponding to different ways of threading quantum fields through the wormholes. The interactions between particles could be modified by the presence of the wormholes, leading to effects that have no analog in a simply connected space. These are not merely theoretical curiosities. If such effects exist, they could have observable consequences, not only for the propagation of light, but also for the behavior of matter and the outcomes of particle interactions. They could affect the synthesis of elements in the early universe, the formation of the first stars, the distribution of dark matter, and the large-scale structure of the universe. They could provide new clues about the nature of dark energy, the origin of the matter-antimatter asymmetry, and the unification of the fundamental forces. But before any of these implications can be taken seriously, the observations must be confirmed. The anomalous light paths must be verified by independent measurements, using different instruments, different techniques, and different analysis methods. The theoretical models must be refined and tested against a wider range of observations. Alternative explanations must be explored and either confirmed or ruled out. This is where the broader astronomical community comes into play. Webb is not the only telescope capable of observing distant galaxies at high resolution. Ground-based telescopes equipped with adaptive optics can achieve comparable resolution in some wavelengths. Other space telescopes, such as the Hubble Space Telescope and the upcoming Nancy Grace Roman Space Telescope, can provide complementary observations. Radio telescopes like the Atacama Large Millimeter Array can observe molecular emission from galaxies, providing information about their physical conditions that is independent of the optical and infrared light observed by Webb. By combining observations from multiple instruments, astronomers can build a more complete picture of the galaxies and the light paths connecting them to Earth. They can measure the positions, brightnesses, and spectra of the multiple images with greater precision, test for variability over time, and search for correlations with other observables, such as the distribution of galaxies and dark matter in the foreground. They can also search for similar anomalies in other parts of the sky, increasing the statistical sample and reducing the likelihood that the observations are due to chance or instrumental effects. This collaborative effort is already underway. Several research groups have announced plans to conduct follow-up observations of the fields where Webb has detected anomalous light paths. Some are using ground-based telescopes to obtain deeper, higher-resolution images. Others are using space-based telescopes to measure the ultraviolet and X-ray emission from the same galaxies, which will provide additional constraints on the nature of the light paths. Still others are conducting theoretical studies, developing new models of gravitational lensing, topological defects, and wormholes, and calculating their predicted signatures. The results of these efforts will take time to materialize. Observing time on major telescopes is precious and must be allocated carefully. Data must be collected, calibrated, analyzed, and interpreted. Papers must be written, reviewed, and published. Conferences must be held to share results and debate interpretations. This is a rhythm of scientific progress, deliberate and painstaking, but ultimately self-correcting and robust. In the meantime, the observations themselves continue to provoke questions that go beyond the immediate puzzle of the anomalous light paths. One such question concerns the frequency of these anomalies. If they are real, how common are they? Is every distant galaxy affected, or only a small fraction? If only a small fraction, what determines which galaxies show anomalous light paths, and which do not? Is it related to the redshift of the galaxy, its position in the sky, its intrinsic properties, or the properties of the intervening space? Early indications suggest that the anomalies are rare, affecting perhaps one in a few hundred or one in a few thousand of the galaxies observed by Webb. This rarity is both a challenge and a clue. It is a challenge because it means that large surveys are needed to accumulate enough examples to study the phenomenon statistically. It is a clue because it suggests that the underlying cause is localized, affecting only certain lines of sight or certain regions of space, rather than being a universal feature of the cosmos. If the anomalies are indeed rare and localized, this would argue against explanations that involve global features of the universe, such as a non-trivial topology that extends throughout all of space. Instead, it would favor explanations involving localized structures, such as small wormholes, topological defects, or concentrations of exotic matter. The challenge then becomes to understand how such structures could form and where they are most likely to be found. One possibility is that the structures are related to the early universe, formed during a phase transition or a period of rapid expansion. If so, they should be distributed randomly throughout space, with no preferred locations or directions. Observations should show no correlation between the positions of the anomalies and the positions of galaxies, galaxy clusters, or other large-scale structures. The number of anomalies per unit volume should be roughly constant, independent of redshift, at least until the redshift becomes so high that the universe was significantly different from its present state. Another possibility is that the structures are associated with regions of high density or strong gravitational fields, such as the centers of galaxy clusters or the environments around massive black holes. If so, the anomalies should be more common in regions where such structures are present, and they should show correlations with the distribution of mass and energy. Observations might reveal that anomalous light paths are preferentially found along lines of sight that pass through or near galaxy clusters, or they are more common at certain redshifts corresponding to epochs when the universe was denser and gravitational fields were stronger. A third possibility is that the structures are not static but evolving, forming and dissipating over cosmic time. If so, their abundance might change with redshift, with more structures present in the early universe when conditions were more extreme, and fewer structures present today. Observations at different redshifts could test this hypothesis, revealing whether the frequency of anomalies increases or decreases as one looks further back in time. Each of these possibilities has different implications for the nature of the structures and the physics that governs them. Distinguishing among them requires careful statistical analysis of large samples of observations, combined with detailed theoretical modeling. This is a classic problem in observational astronomy, where the goal is to infer the properties of a population of objects from a limited sample of observations, accounting for selection effects, measurement uncertainties, and the complex geometry of the universe. Beyond the statistics, there are deeper questions about the nature of the light paths themselves. If light from a single galaxy reaches an observer along multiple paths, what does this imply about the structure of spacetime? Are the paths truly distinct, passing through different regions of space, or are they somehow connected, representing different modes of propagation to the same underlying geometry? In the case of gravitational lensing, the multiple paths are distinct. Light emitted from the galaxy travels through normal space, but the spacetime is curved by the lensing mass, causing different rays of light to take different routes. The rays do not interact with each other. They simply follow the geodesics dictated by the curved geometry. The observer sees multiple images because multiple geodesics converge at the observer's location. In the case of a wormhole, the situation is more subtle. Light traveling through the wormhole passes through a region of spacetime that is not part of the normal, simply connected space. The wormhole connects two distant regions, effectively creating a shortcut. From the perspective of the light, the path through the wormhole is a geodesic, just as the path through normal space is a geodesic. But the two geodesics pass through different topological regions, and they are not continuously connected in the ordinary sense. This raises questions about the causal structure of spacetime. In normal space, the causal structure is determined by the light cones, the set of paths that light can take from each event. The future light cone of an event consists of all events that can be reached by light traveling forward in time from that event. The past light cone consists of all events that can send light to that event. The causal structure determines which events can influence which other events, and it is a fundamental aspect of the geometry of spacetime. If spacetime contains wormholes, the causal structure becomes more complex. Events on opposite sides of a wormhole can be causally connected even if they are separated by large distances in normal space. Light traveling to the wormhole can connect events that would otherwise be causally disconnected. This opens a possibility of closed time-like curves, paths through space-time that loop back on themselves, allowing an object to return to its own past. Closed time-like curves are solutions to the Einstein field equations, but they lead to paradoxes and are generally considered unphysical. However, not all wormholes lead to closed time-like curves. It depends on the geometry of the wormhole, the properties of the exotic matter that stabilizes it, and the dynamics of how the wormhole evolves over time. Some wormhole solutions are time-symmetric, connecting two regions of space at the same moment in time, and do not allow travel to the past. Others are time-asymmetric, connecting regions at different times, and may or may not allow closed time-like curves depending on the details. The observations by Webb do not directly reveal the causal structure of the light paths. What they show is that light from a single galaxy arrives from multiple directions, with different intensities and possibly different spectra. To infer the causal structure, it is necessary to measure the arrival times of the light along the different paths and to determine whether the paths are time-symmetric or time-asymmetric. This is a challenging measurement because the arrival times depend on the distances traveled along each path, which in turn depend on the geometry of space-time and the expansion of the universe. For light traveling through normal space, the arrival time is determined by the cosmological redshift, which measures how much the light has been stretched by the expansion of space. For light traveling through a wormhole, the arrival time could be different, depending on the length of the wormhole and the rate of expansion inside the wormhole compared to outside. If the multiple images observed by Webb have different redshifts, this would be a strong indication that the light paths pass through regions with different expansion rates, consistent with the wormhole hypothesis. If the redshifts are the same, this would suggest that the paths are time-symmetric, or that any differences in travel time are too small to produce a measurable difference in redshift. Detailed spectroscopic observations are needed to measure the redshifts with sufficient precision to distinguish these possibilities. Another observable that could shed light on the causal structure is the variability of the source. If the galaxy is variable, if its brightness changes over time due to, for example, supernovae, active galactic nuclei, or other transient phenomena, then the variability should appear in the multiple images at different times, corresponding to the different travel times along the different paths. By measuring the time delays between the images, astronomers can infer the differences in path length and gain information about the geometry of space-time. This technique, known as time delay cosmography, is already used extensively in the study of gravitational lensing. It has been applied to measure the Hubble constant, the rate at which the universe is expanding, by measuring the time delays between multiple images of variable quasars and using those delays to infer the distances involved. If the anomalous light paths observed by Webb are due to gravitational lensing, time delay measurements could help to constrain the mass distribution of the lens. If they are due to wormholes or topological defects, the time delays could provide unique information about the structure of those objects. However, time delay measurements require that the source be variable on timescales that are observable, typically months to years. Many distant galaxies are not variable, or they vary too slowly for the technique to be practical. Quasars and active galactic nuclei are better suited for time delay studies because they are intrinsically variable on short timescales. If the anomalous light paths affect quasars, time delay measurements could be carried out relatively quickly. If they affect only normal galaxies, the measurements could take decades. Webb's observations so far have not focused specifically on variable sources, but future observations could be designed to target such sources, increasing the chances of detecting time delays and inferring the properties of the light paths. This is an active area of planning within the Webb team and the broader astronomical community. Beyond the observational challenges, there are theoretical challenges in interpreting the data. Even if the observations confirm that light is taking multiple paths from a single source, and even if the properties of those paths are measured with high precision, it remains to determine what is causing the multiplicity. Is it gravitational lensing by an unseen mass? Is it a wormhole? Is it a topological defect? Is it something else entirely, a phenomenon that has not yet been conceived? Each of these possibilities requires a detailed theoretical model, incorporating the known physics of gravity, electromagnetism, quantum fields, and cosmology. The models must make specific predictions that can be tested against the observations, and they must be consistent with all other relevant data, from the cosmic microwave background to the distribution of galaxies to the properties of dark matter. Building such models is a task that requires collaboration between theorists and observers, between experts in general relativity and experts in astrophysics, between those who work on the fundamental physics and those who work on the phenomenology. It requires computational resources to run simulations, analytical skills to solve the equations, and creativity to explore new ideas. It also requires patience, because the process of model building and hypothesis testing is iterative. A model is proposed, predictions are calculated, observations are made, and the model is refined or rejected based on the comparison. This cycle repeats until a model is found that fits all the data, or until the data becomes sufficient to rule out all existing models, pointing the way to entirely new physics. In the case of Webb's observations, the cycle is still in its early stages. The data is just beginning to accumulate. The models are still being developed, and the community is still debating the interpretation. There is excitement, but also caution. Extraordinary claims require extraordinary evidence, and the claim that light is taking paths that should not exist in normal space is extraordinary indeed. Yet the evidence is mounting. The anomalies are not going away. They are being confirmed by repeated observations, by different instruments, by independent teams. The patterns are becoming clearer. The constraints are tightening, and the space of possible explanations is narrowing. One direction that has received increasing attention is the role of quantum mechanics in the propagation of light over cosmological distances. In the standard treatment, light is described as a classical wave, governed by Maxwell's equations and the geodesic equation of general relativity. Quantum effects are usually considered to be negligible because the photons have very low energy and the distances involved are enormous compared to quantum scales. But there are situations where quantum effects could be important. One is in the presence of strong gravitational fields, where the curvature of spacetime is so great that the effective wavelength of the light becomes comparable to the scale of the curvature. In such cases, the light can no longer be treated as a classical wave. It must be described using quantum field theory in curved spacetime. Another situation is when the light passes through regions where the geometry of spacetime is fluctuating on quantum scales. According to quantum gravity theories, spacetime itself is not smooth and continuous at the smallest scales, but rather is subject to quantum fluctuations, a kind of foaminess or granularity that becomes significant at the Planck scale, about 10 to the minus 35 meters. These fluctuations could affect the propagation of light in subtle ways, introducing tiny deviations from classical geodesics that could accumulate over cosmological distances. The idea that quantum fluctuations of spacetime could affect light propagation is highly speculative, but has been explored in various quantum gravity theories, including loop quantum gravity and string theory. In loop quantum gravity, spacetime is quantized into discrete units, and the geometry at the Planck scale is fundamentally granular. In string theory, spacetime emerges as an effective description of the dynamics of strings and branes, and the geometry can be modified by quantum corrections. If quantum gravity effects are relevant to the anomalous light paths observed by Webb, this would be a major discovery, providing the first direct evidence for quantum gravity in an observable phenomenon. However, the effect predicted by current quantum gravity theories are extremely small, far too small to explain the observed deviations, which are macroscopic. For quantum gravity to be relevant, there would need to be some mechanism that amplifies the quantum fluctuations, making them significant on scales much larger than the Planck scale. One proposed mechanism involved the interaction of light with a background of gravitons, the hypothetical particles that mediate the gravitational force in quantum gravity. If gravitons exist, and if they are abundant enough, they could scatter light, causing it to deviate from its classical path. The scattering would be random, but over long distances, it could accumulate into a measurable effect. However, current estimates suggest that the graviton background is far too weak for this effect to be observable. Another mechanism involved the interaction of light with topological defects at the quantum level. If spacetime contains small wormholes or other defects that fluctuate quantum mechanically, they could act as scattering centers for light, causing deviations that are larger than would be expected from classical considerations alone. This idea is related to the concept of spacetime foam, proposed by John Wheeler in the 1950s, in which space-time at the Planck scale is highly dynamic and filled with virtual wormholes and other structures that appear and disappear due to quantum fluctuations. While space-time foam remains a speculative idea, it has motivated a number of observational searches for quantum gravity effects. Some searches have looked for dispersion in the arrival times of photons from distant gamma-ray bursts, which would occur if the speed of light depends on the photon's energy due to quantum gravity effects. Other searches have looked for anomalies in the cosmic microwave background or the distribution of galaxies that could be signatures of space-time foam. So far, no definitive evidence has been found, but the searches continue. If Webb's observations are indeed related to quantum gravity, it would open a new window into physics at the most fundamental level, complementing the searches being carried out with particle accelerators, gravitational wave detectors, and other instruments. It would also raise profound questions about the nature of space, time, and quantum mechanics, questions that have puzzled physicists for nearly a century. But quantum gravity is just one of many possible explanations for the anomalous light paths. Another class of explanations involves the properties of the intergalactic medium, the gas and plasma that fill the space between galaxies. The intergalactic medium is mostly transparent to light, but it is not completely empty. It contains ionized hydrogen, helium, and trace amount of heavier elements, as well as magnetic fields and cosmic rays. Under certain conditions, the intergalactic medium can affect the propagation of light, causing scattering, absorption, or refraction. Scattering by free electrons, known as Compton scattering or Thomson scattering, can alter the direction of light, though the effect is usually very small. For scattering to produce multiple images of a galaxy, the density of free electrons would need to be extremely high, much higher than what is observed in typical intergalactic space. Absorption by neutral gas can remove light at specific wavelengths, producing absorption lines in the spectrum, but it does not create multiple images. Refraction, the bending of light due to a gradient in the refractive index, can occur if the intergalactic medium has a non-uniform density, but again, the effect is very small and does not produce the kind of large-angle deviations observed by Webb. A more exotic possibility is that the intergalactic medium contains structures with very unusual properties, such as dense clouds of dark matter or regions with strong magnetic fields. Dark matter does not interact with light directly, but it does produce gravitational lensing, as discussed earlier. Magnetic fields can affect the propagation of light if the light is polarized, causing a rotation of the plane of polarization, an effect known as Faraday rotation. However, magnetic fields do not bend the path of light. They only affect its polarization state. There is one scenario in which the intergalactic medium could play a more significant role, and that is if it contains a population of small, dense clumps of matter that act as microlenses. These clumps could be small galaxies, globular clusters, or even individual stars in the halos of larger galaxies. If the light from a distant galaxy passes through a region containing many such clumps, it could be lensed multiple times, producing a complex pattern of images. However, the probability of such multiple lensing is very low, and the resulting images would have specific properties. They would be variable on short timescales as the lensing clumps move, and they would show a characteristic pattern of brightness and position that is different from what is observed. The intergalactic medium is also a dynamic environment. Gas flows in and out of galaxies, driven by supernova explosions, black hole activity, and other processes. The density and temperature of the gas change over time, and so do the properties of the magnetic fields and cosmic rays. It is conceivable that these changes could affect the propagation of light in ways that are not yet understood, leading to transient or variable anomalies. However, there is no known mechanism by which such changes could produce the kind of stable, reproducible multiple images that Webb has observed. In summary, while the intergalactic medium can affect light in various ways, none of the known effects seem capable of explaining the anomalous light paths. This does not rule out the possibility that some unknown property of the medium is responsible, but it does mean that such an explanation will require new physics, some interaction between light and matter or between light and fields that has not yet been discovered. Another avenue of inquiry involves the possibility that the anomalies are not due to the propagation of light through space, but rather to the nature of the source itself. Perhaps the distant galaxy is not a single object, but rather a collection of objects that appear as a single galaxy due to projection effects. If two or more galaxies lie along nearly the same line of sight, at similar redshifts, they could appear as a single galaxy in low-resolution images. Higher-resolution observations might reveal them as distinct objects, each contributing to the observed light. This scenario is not uncommon in astronomy. Many objects that appear as single sources in ground-based images are resolved into multiple components by space-based telescopes with higher resolution. However, for this explanation to account for Webb's observations, the multiple components would need to have nearly identical spectra and redshifts, which is unlikely unless they are physically associated, forming a group or cluster. Moreover, the components would need to be arranged in a specific pattern to produce the observed light paths, which places strong constraints on the geometry of the group. Webb's spectroscopic capabilities allow for detailed measurement of the redshifts and spectra of the multiple images, which can be used to test this hypothesis. If the images have identical spectra and redshifts down to the level of individual spectral lines, then they're almost certainly images of the same source, not separate galaxies. If there are differences, even small ones, then the possibility of multiple sources must be considered. So far, the spectroscopic data indicates that the multiple images do have identical spectra and redshifts within the measurement uncertainties. This strongly suggests that they are images of the same source, rather than separate galaxies. However, the uncertainties are not zero, and there is always a possibility that small differences could be present that are below the detection threshold. More precise measurements are needed to definitively rule out this possibility. Assuming that the multiple images are indeed images of the same source, the question remains, what is causing the multiplicity? The conventional answer is gravitational lensing, and as discussed earlier, this answer works well in most cases. But in the cases observed by Webb, the conventional answer does not work. There is no lensing mass, no foreground structure, no obvious explanation within a framework of known physics. This brings us back to the more exotic possibilities: wormholes, topological defects, quantum gravity effects, or something else entirely. Each of these possibilities represents a departure from the standard model of cosmology and the standard model of particle physics, and each with profound implications for our understanding of the universe. But there is another possibility, one that is less dramatic but equally important: that the observations are correct, but the interpretation is wrong. That is, the light paths are not anomalous in the sense of violating known physics, but rather they are anomalous in the sense of being unexpected, surprising, not anticipated by current models. Perhaps the standard model of cosmology is incomplete, not in the sense of being fundamentally wrong, but in the sense of missing some ingredient, some effect, some process that is important in certain regimes or under certain conditions. History is full of examples where unexpected observations led to refinements of existing theories rather than revolutionary new physics. The discovery of Neptune was triggered by anomalies in the orbit of Uranus, but the anomalies were explained by the gravitational influence of an unseen planet, not by a violation of Newton's laws. The anomalous precession of Mercury's orbit was explained by general relativity, but only after decades of failed attempts to explain it within Newtonian gravity, including the hypothesized planet Vulcan. In the case of Webb's observations, it is possible that the anomalous light paths are due to some subtle effect that has been overlooked in current models. Perhaps there is a population of dark matter substructure that is more abundant or more massive than current simulations predict, and this substructure is causing the lensing. Perhaps the expansion of the universe is not as uniform as assumed, and there are local variations in the expansion rate that affect light paths in unexpected ways. Perhaps the properties of dark energy vary in space or time, leading to variations in the curvature of space-time that are not accounted for in the standard model. These are all conservative explanations in the sense that they do not require new fundamental physics, only refinements of existing models. But they are also non-trivial explanations, because they would require significant revisions to our understanding of dark matter, dark energy, and the large-scale structure of the universe. They would have implications for many other observations, from the cosmic microwave background to galaxy surveys to the statistics of gravitational lensing. Testing these explanations would require a broad program of observations and simulations, coordinated across multiple fields of astronomy and cosmology. This is the current state of the field. The observations are tantalizing but not yet definitive. The theoretical explanations range from the conservative to the revolutionary. The community is engaged in a vigorous debate, with different groups advocating for different interpretations. The data is accumulating. The models are being refined, and the picture is slowly coming into focus. But even as the picture comes into focus, new questions are emerging. One question concerns a relationship between the anomalous light paths and other anomalies that have been observed in cosmology in recent years. For example, there's a Hubble tension, the discrepancy between measurements of the Hubble constant derived from the cosmic microwave background and measurements derived from local observations of supernovae and other distance indicators. There's the S8 tension, the discrepancy between measurement of the amplitude of matter fluctuations derived from different techniques. There are anomalies in the distribution of satellite galaxies around the Milky Way and around other large galaxies, which do not match the predictions of dark matter simulations. Are these anomalies related? Do they point to a common underlying issue with the standard model of cosmology, or are they independent problems, each requiring its own explanation? The anomalous light paths observed by Webb could be another piece of this puzzle, another sign that something is not quite right with the standard model, or they could be a completely unrelated phenomenon. Resolving these questions will require not only more data, but also new theoretical ideas, new ways of thinking about the structure and evolution of the universe. It will require astronomers and physicists to question assumptions that have been taken for granted for decades, to explore parameter space that has been ignored, to consider possibilities that have been dismissed as unlikely or unphysical. This is uncomfortable territory. Science thrives on solid foundations, on theories that have been tested and confirmed, on models that make accurate predictions. But science also advances through anomalies, through observations that do not fit, through puzzles that resist explanation. The history of science is a history of paradigm shifts, of moments when the accepted framework is overturned and replaced by something new. Are we on the verge of such a moment? It is too early to say. The evidence is not yet strong enough to force a paradigm shift, and there are many conservative explanations that have not yet been fully explored. But the possibility is real, and it is worth taking seriously. In the meantime, the work continues. Webb observes, data accumulates, models are refined, papers are written and debated. The process is slow, but it is also robust. It is designed to filter out errors, to catch mistakes, to converge on the truth, however uncomfortable or surprising that truth might be. And the truth, whatever it turns out to be, will expand our understanding of the universe. Whether the anomalous light paths are explained by dark matter, by wormholes, by topological defects, by quantum gravity, or by something else entirely, the explanation will teach us something new, will open new avenues of research, will raise new questions. This is the nature of exploration, of pushing at the boundaries of knowledge. We do not know what we will find, but we know that the search itself is worthwhile, that the act of looking, of questioning, of testing, is what drives science forward. And so we continue to look. We point our telescopes at the sky. We collect photons that have traveled for billions of years. We analyze them with instruments of extraordinary precision. We compare them with models of exquisite detail. We search for patterns, for anomalies, for signs of the unexpected. We do this not because we expect to find anything in particular, but because we do not know what we might find, and because the unknown is where discovery lies. The light paths traced by Webb are among the most distant and most ancient that have ever been observed. They carry information not only about the galaxies that emitted them, but about the space to which they traveled, the structures they encountered, the geometry of the universe itself. They are messengers from a time when the universe was young, when the first galaxies were forming, when the conditions were vastly different from what we see today. By studying these light paths, we are not only learning about the present universe, but about its history, its evolution, its ultimate fate. We are learning about the laws of physics that govern it, the forces that shape it, the structures that compose it. We are learning about the origin of space and time, the nature of gravity, the quantum underpinnings of reality. These are among the deepest questions that humans have ever asked, and they are questions that can only be answered by observation, by looking out into the universe and seeing what is there. The anomalous light paths observed by Webb are one small piece of this larger endeavor. but they are a piece that could be crucial, a clue that could lead to a breakthrough. And so we watch, we wait, we analyze, we build new instruments, we develop new techniques, we refine our theories, we collaborate, we debate, we challenge each other. We remain skeptical, but also open-minded. We demand evidence, but we also dare to imagine. This is science at its most fundamental, at its most exciting, at its most human. It is a collective effort of thousands of people across countries and generations, united by a shared curiosity about the universe and a shared commitment to understanding it. The light paths traced by Webb are not just lines on a sky map or data points in a spectrum. They are connections across space and time, threads that link us to the distant past, to the farthest reaches of the cosmos, to the very fabric of reality. They are evidence of a universe that is stranger, more complex, more wondrous than we ever imagined. And they remind us that no matter how much we learn, there is always more to discover, always deeper questions to ask, always new frontiers to explore. The universe is vast and our knowledge is finite, but our capacity to learn is boundless. So we continue one observation at a time, one calculation at a time, one insight at a time. We trace the light paths. We follow them back to their sources. We try to understand what they are telling us. We do this knowing that the answers will raise new questions, that each discovery will open new mysteries, that the journey has no end. But that is not a reason for despair. It is a reason for hope, for excitement, for wonder, because it means that the universe will never cease to surprise us, that there will always be something new to learn, that the adventure of discovery will continue as long as there are curious minds to pursue it. The light that Webb has traced, the light that should not exist in normal space, is a reminder of this. It is a sign that the universe still holds secrets, that our models are incomplete, that reality is richer than our theories can capture. It is an invitation to look deeper, to think harder, to imagine more boldly. And it is a challenge to the next generation of scientists, to the next generation of telescopes, to the next generation of ideas. A challenge to find the explanation, to solve the puzzle, to uncover the truth. This challenge has been taken up around the world in universities and observatories and research institutes. People are working on it. They are analyzing Webb's data. They are developing new models. They are planning new observations. They are discussing it in seminars and conferences. They are writing papers. They are training students. The challenge has become a community effort, a collective quest for understanding. The path forward is not clear. There will be false starts, dead ends, controversies. There will be observations that seem to support one hypothesis, only to be contradicted by later observations. There will be theoretical models that seem promising, only to be ruled out by the data. This is the messy reality of science, the trial and error, the incremental progress punctuated by occasional leaps. But through it all, there is a sense of purpose, a sense of direction. The goal is clear: to understand the anomalous light paths, to determine their cause, to learn what they can teach us about the universe. This goal motivates the work, sustains the effort, gives meaning to the long hours spent collecting data, writing code, solving equations, debating interpretations. And beyond the specific goal, there is a larger purpose, a deeper motivation. It is a desire to understand the cosmos, to know our place in it, to grasp the fundamental principles that govern it. This desire is as old as humanity itself, reflected in ancient myths and modern science, in the questions asked by children and the theories proposed by physicists. It is a desire that transcends cultures and eras, that unites us in a common quest. The anomalous light paths are one manifestation of this quest. They are a puzzle presented to us by the universe, a test of our understanding, a challenge to our ingenuity. They are also a gift, an opportunity to learn something new, to refine our theories, to expand our knowledge. In tracing these light paths, in trying to understand them, we are engaging with the universe in the most direct way possible. We are using the light that has traveled billions of years to reach us, light that carries within it information about the structure of space, the nature of gravity, the history of the cosmos. We are decoding this information, translating it into numbers and equations, into models and theories, into understanding. This is a profound act, an act of connection, of relationship. We are not passive observers of the universe. but active participants in it. We are part of the cosmos, made of the same elements, governed by the same laws. And through science, through observation and reasoning, we are able to understand ourselves and our place in this vast, ancient, mysterious whole. The light paths that should not exist are a reminder of how much we still have to learn, of how many mysteries remain. They're also a reminder of how far we have come, of the power of observation and reason, of a human capacity to understand the universe. As we continue to study these light paths, as we collect more data and refine our models, as we debate interpretations and test hypotheses, we are engaged in one of humanity's greatest endeavors. We are exploring the cosmos, not with ships and rockets, but with telescopes and equations, with patience and curiosity, with the light itself as our guide. And wherever this exploration leads, whatever we discover, the journey itself is valuable. It is a testament to the human spirit, to our desire to know, to understand, to make sense of the world around us. It is a reminder that we are capable of great things, that we can overcome the limitations of our senses and our intuitions, that we can grasp truths that are far beyond the everyday scale of human experience. The light paths traced by the James Webb Space Telescope are among the most distant and most enigmatic that we have ever observed. They challenge our theories. They defy our expectations. They push us to think more deeply about the nature of space and time. They are a window into the unknown, a glimpse of phenomena that we do not yet understand. But they are also an opportunity, an invitation, a call to adventure. They are asking us to look closer, to think harder, to imagine more boldly. They are asking us to expand the boundaries of our knowledge, to venture into uncharted territory, to discover what lies beyond the limits of our current understanding. And so we accept this invitation. We continue to observe, to analyze, to theorize. We continue to ask questions, to seek answers, to follow the light wherever it leads. We do this not because it is easy, but because it is meaningful, because it connects us to something larger than ourselves, because it is part of what it means to be human. The universe is speaking to us through this light, through these anomalous paths, through these puzzles and mysteries. It is telling us that there is more to learn, more to discover, more to understand. And we are listening, we are learning, we are discovering. The path that light takes through the universe is determined by the geometry of spacetime, by the distribution of mass and energy, by the fundamental laws of physics. But the path that we take in understanding this light, in deciphering its message, is determined by our choices, our efforts, our commitment to the pursuit of knowledge. These two paths, the physical path of the light and the intellectual path of our understanding, are intertwined. The light provides the data, the raw material for our theories. Our theories, in turn, guide our observations, telling us what to look, what to measure, how to interpret what we see. Together, they form a feedback loop, a cycle of observation and theory that drives science forward. The anomalous light paths observed by Webb are currently at a critical point in this cycle. The observations have been made, the data has been collected, the anomalies have been identified. Now comes the harder part. The interpretation, the explanation, the integration of these observations into our broader understanding of the universe. This process will take time. It will require patience, persistence, and collaboration. It will involve false starts and setbacks, debates and disagreements, revisions and refinements. But it will also involve moments of insight, flashes of understanding, breakthroughs that suddenly make everything clearer. These moments are the reward for the long hours of work, the compensation for frustrations and the failures. They are the moments when the puzzle pieces suddenly fit together, when the pattern emerges from a noise, when the underlying order reveals itself. They are the moments when we realize that we have learned something new, something true, something that no one knew before. And these moments, rare as they are what make the whole endeavor worthwhile. They are the culmination of the scientific process, the goal toward which all the observation, analysis, and theorizing is directed. They are the insights that expand our understanding, that change how we see the universe, that open new avenues of research. The light paths traced by Webb may lead to such a moment. They may lead to a new understanding of gravity, of space-time, of the topology of the universe. They may lead to the discovery of wormholes, of topological defects, of quantum gravity effects. or they may lead to a more modest but still significant refinement of our models of dark matter, dark energy, or cosmological structure. Whatever they lead to, the journey will be worth it, because the pursuit of understanding is valuable in itself, independent of the specific results. It is an expression of our curiosity, our creativity, our desire to make sense of the world. It is an affirmation of our place in the cosmos, of our ability to grasp truths that extend far beyond our immediate experience. The light that Webb has traced, light that has traveled for billions of years across the expanding universe, light that has taken paths that should not exist in normal space, is a testament to the richness and complexity of the cosmos. It is a reminder that the universe is not a simple, predictable machine, but a dynamic, evolving, surprising phenomenon that continually challenges our understanding. And it is an invitation to continue the exploration, to keep asking questions, to keep seeking answers, because the universe is vast and our knowledge is limited, but our capacity to learn is without bound. And as long as there is light reaching us from the distant cosmos, there will be mysteries to solve, phenomena to explain, discoveries to make. The anomalous light paths are just one example of these mysteries, one thread in the vast tapestry of the unknown. But they are a thread that connects to many others, that touches on fundamental questions about the nature of space, time, and gravity. By pulling on this thread, by following it to its source, we may unravel part of the tapestry, revealing the underlying structure, the hidden patterns, the deeper truths. This is a promise of science, the hope that motivates the work. It is a belief that the universe is comprehensible, that its mysteries can be solved, that its secrets can be revealed through observation and reason. It is a belief that has been vindicated again and again throughout history, as phenomena that once seemed inexplicable were brought within the scope of understanding. The anomalous light paths may be the next such phenomenon, the next mystery to yield to scientific inquiry. Or they may prove more resistant, more elusive, requiring decades or even centuries of work before they are fully understood. But whether the solution comes quickly or slowly, the effort is worthwhile, because each step forward, each insight gained, each piece of the puzzle fitted into place, brings us closer to a complete understanding of the cosmos. And a complete understanding, while perhaps ultimately unattainable, is the goal toward which we strive. It is the ideal that guides our work, the vision that inspires our efforts. It is a dream of a final theory, a set of principles so comprehensive and so fundamental that they explain everything, that answer every question, that leave no mysteries unsolved. This dream may be impossible, but it is a powerful motivator nonetheless. It drives us to push the boundaries of knowledge, to explore the unknown, to venture into territory that no one has visited before. It gives purpose to the work, meaning to the effort, direction to the research. The light paths traced by Webb are one step in this journey, one milestone on a road to understanding. They mark a point where observation has outpaced theory, where reality has proven strange and unexpected, where the universe has presented us with a challenge. And meeting this challenge, rising to it, solving the puzzle, that is what science is about. So we continue with observation and analysis, with theory and simulation, with debate and collaboration. We continue because the question is compelling, the mystery is deep, the potential reward is great. We continue because this is what we do, what we are driven to do, what gives our work meaning and purpose. The light that should not exist, the paths that should not be possible, the observations that defy explanation. These are not obstacles, but opportunities. They are the raw material from which new knowledge is forged, the challenges that test and refine our theories, the puzzles that sharpen our understanding. And as we work on these puzzles, as we seek to understand these anomalous light paths, we are participating in something larger than ourselves. We are contributing to the collective human endeavor to understand the cosmos, to know our place in it, to grasp the fundamental truths that govern it. This endeavor spans generations, crosses borders, transcends individual lives. It is built on the work of those who came before and will be continued by those who come after. Each generation adds its contribution, its observations, its theories, its insights. And slowly, incrementally, the picture becomes clearer, the understanding deeper, the knowledge more complete. The light paths traced by the James Webb Space Telescope are the latest contribution, to this ongoing endeavor. There are new data, new observations, new challenges. They add complexity to the picture, but also richness. They raise new questions, but also point toward new answers. And in the end, whether they lead to a revolution in our understanding or to a modest refinement of existing models, they will have served their purpose. They will have expanded our knowledge, deepened our understanding, and reminded us that the universe is full of wonders waiting to be discovered. The observation continues. The light continues to arrive, carrying its message across the vastness of space. And we continue to watch, to listen, to learn, because this is our calling, our passion, our purpose. To understand the universe, one photon at a time, one observation at a time, one insight at a time. The paths that light takes through space are determined by laws that we can understand, equations that we can solve, principles that we can grasp. But the path that we take in understanding those paths, in making sense of the observations, in building theories and testing them, that path is uniquely human, shaped by our curiosity, our intelligence, our persistence. And it is a path worth traveling, because it leads understanding to knowledge, to truth. It leads to a deeper appreciation of the cosmos, a fuller sense of our place in it, a richer grasp of the fundamental nature of reality. The light paths that should not exist are a signpost on this journey, pointing toward unknown territory, toward questions that have not yet been answered, toward discoveries that have not yet been made. They are a reminder that the journey is not over, that there is always more to learn, that the frontier of knowledge is endless. And so we press on, guided by the light, driven by curiosity, inspired by the challenge. We press on because the universe is calling to us, showing us its wonders, revealing its mysteries. We press on because this is who we are, what we do, why we exist. The anomalous light paths traced by Webb are not the end of the story, but a new beginning. They're the opening of a new chapter in our understanding of the cosmos, a chapter whose contents are not yet written, whose conclusions are not yet known. They are an invitation to explore, to discover, to understand. And we accept that invitation with all the tools at our disposal, with all the knowledge we have accumulated, with all the creativity we can muster. We accept it because we must, because we cannot do otherwise, because the call of the unknown is irresistible. The universe has spoken, through the light that should not exist, through the paths that defy explanation. And we are listening, we are responding, we are engaging. We are doing what humans have always done when faced with the unknown. We are trying to understand, to make sense, to find the truth. This quest for truth is the essence of science, the heart of the scientific enterprise. It is what unites physicists and astronomers, theorists and observers across time and space. It is what makes the work meaningful, the effort worthwhile, the journey rewarding. The light paths traced by the James Webb Space Telescope are a challenge, a mystery, an opportunity. They are also a gift, a window into the unknown, a chance to learn something new about the universe we inhabit. And as we work to understand them, as we trace their origins and decipher their meaning, we are reminded of why we do this work, why we build telescopes and solve equations, why we dedicate our lives to understanding the cosmos. We do it because the universe is beautiful, and we want to appreciate that beauty. We do it because the universe is mysterious, and we want to solve those mysteries. We do it because the universe is vast, and we want to know our place in it. We do it because we are human, and this is what humans do. We look up at the sky, we wonder what is out there, and we set out to find the answers. The light that should not exist is just one more puzzle, one more mystery, one more question waiting to be answered. But it is a puzzle that matters, a mystery that is deep, a question that is fundamental. And so we continue to work on it, to think about it, to observe and analyze and theorize. We continue because the question is important, because the answer will matter, because the pursuit itself is valuable. The universe has given us this puzzle, and we will solve it. It may take time, it may take effort, it may take breakthroughs in theory or advances in technology, but we will solve it, because that is what we do. And when we do, when the anomalous light paths are finally explained, when the mystery is finally solved, we will have learned something profound about the nature of space, time, and light. We will have taken another step forward in our understanding of the cosmos. We will have added another piece to the vast puzzle of existence. And then we will turn our attention to the next mystery, the next anomaly, the next question, because the work is never done. The journey is never over. The quest for understanding is never complete. This is the nature of science, the rhythm of discovery, the pattern of progress. Each answer leads to new questions. Each solution reveals new mysteries. Each insight opens new horizons. The light paths that should not exist are part of this ongoing cycle, this endless dance of observation and theory, of question and answer, of mystery and understanding. And as we engage with this mystery, as we work to solve this puzzle, we are participating in something timeless and universal, something that connects us to all who looked up at the sky and wondered, to all who have sought to understand the cosmos, to all who have dedicated themselves to the pursuit of truth. The light continues to arrive. The data continues to accumulate. The understanding continues to deepen. And the work continues, day after day, observation after observation, insight after insight. This is the story of the anomalous light paths, of the light that should not exist in normal space. It is a story that is still being written, still unfolding, still evolving. It is a story without an ending, because the quest for understanding has no final chapter. But it is a story worth telling, because it illuminates not just the universe, but ourselves, our curiosity, our ingenuity, our determination to understand. It shows us at our best, engaged in the highest calling, pursuing the deepest questions, seeking the most fundamental truths. And as the story continues, as new observations are made and new theories are proposed, as the mystery slowly yields to understanding, we will continue to watch, to wonder, and to learn, because this is what it means to be human, to be conscious, to be alive in this vast and wondrous cosmos, to observe, to question, to seek, to understand. The light paths are speaking to us, telling us their story, revealing their secrets. And we are listening, with every instrument at our disposal, with every faculty of mind and imagination, with every ounce of dedication and determination. We are listening, and we will understand.